Hello again, everyone. Welcome to another episode of Fun with the E6B. In this video, I will show you how to make some airspeed corrections, altitude corrections, and determine your density altitude. So on the face of the E6B, you will probably notice that there are a couple of windows. So one on the left side here, and two on the right side of the face of the E6B. And then there's also a short paragraph on both the left side and the right side there. So the right side is labeled airspeed correction. So these windows that are above that paragraph will be used for airspeed correction. On the left side of the E6B, it's labeled altitude correction, so the window on the left side will be used to correct your altitude. It is important that you do not cross over here. So these windows on the right side of the E6B are not to be used for altitude correction, and the window on the left side of the E6B is not to be used for airspeed correction. So make sure you're using the window on the same side as the guides that are below it. So what do we mean by airspeed and altitude correction? So in terms of an airspeed correction, we can use the E6B to convert between a true airspeed and a calibrated airspeed, and we can also determine our density altitude as well. In terms of altitude correction, we can convert between true altitude, which is our height above mean sea level, and our calibrated altitude, which we'll talk more about in a moment. So the first thing we'll try here is our airspeed corrections and density altitude calculations. So our calibrated airspeed, a reminder of what that is. Calibrated airspeed is simply your indicated airspeed corrected for instrument and position error. So your airspeed indicator determines your airspeed using pressure within the pitot tube and the static port. Unfortunately, it is impossible to have those ports in a perfect location where it is not susceptible to some level of error. They are placed in locations where the error is reduced as much as possible, but you can never totally eliminate the error in the airspeed indicator. So calibrated airspeed is a much more accurate representation of the dynamic pressure that is flowing over the wings, and that is what we use for to determine our lift. So indicated airspeed gets us pretty close to that, but calibrated airspeed is a much more accurate representation of the lift being generated over the wing. So true airspeed is a little bit different. In subsonic flight, true airspeed is simply your calibrated airspeed corrected for temperature and pressure, or in other words, true airspeed is your calibrated airspeed corrected for density. So true airspeed gives you a true measurement of the speed of the aircraft in relation to the air mass that it is flying within. True airspeed is important for performance calculations and time calculations, but it's not really important for aerodynamic considerations, because the true airspeed doesn't really describe the amount of dynamic pressure that the wing is experiencing. It just is simply the speed of the air in relation to the aircraft. Density altitude, a reminder on that. So density altitude is your pressure altitude corrected for non-standard temperature. So if you recall pressure altitude is your height above the standard datum plane, and the standard datum plane is the altitude where you will find 29.92 inches of mercury for any particular day. So pressure altitude is a fairly reliable indicator of how your aircraft will perform. The aircraft will perform as if it is at this altitude. That's essentially what your pressure altitude is. So if your pressure altitude is 3,000, that means you're 3,000 feet above 2992, so the aircraft will behave as if it is at 3,000 feet. Density altitude, on the other hand, is a bit more of an accurate indicator of performance, because density altitude also takes into consideration the temperature as well as the pressure. So before we get started here, again, the scales on the E6B, your outer scale is the A scale, and the middle scale here is the B scale. We are not concerned with the C scale for these calculations. We will not use the C scale. We will obviously use the windows on the face of the E6B, but we will not use the C scale. So we're only concerned with the A scale, the B scale, and the windows on the face of the E6B. So to make these calculations, we need to align our pressure altitude with our temperature using the windows, and then we can read our density altitude above, and we can look at the A and B scales to convert between true airspeed and calibrated airspeed. So in our first example, we will say that we have a calibrated airspeed of 150 knots. By the way, to convert between indicated and calibrated airspeed, you can consult the POH for your aircraft. There should be a table or a graph chart of some kind that will give a conversion factor to convert between indicated and calibrated airspeed. So as we said, 150 knots calibrated airspeed. Now if we look on the B scale, you may notice near between the 25 and the 30, it says CAS, and then on the A scale it says TAS. So all of your calibrated speeds will be found on the B scale. All of your true speeds would be read off of the A scale. So again, 150 knots calibrated airspeed. So we can find that on the B scale. Since the B scale is for calibrated airspeed, we'll use the number 15 to represent 150. Temperature is 15 degrees Celsius. So we are looking at the air temperature scale on the right side of the front of the E6B. So you notice the number 0 here. If you look to the left of the 0, these are actually positive values. To the right of the 0 are negative values, which can be a little bit confusing. That's not traditionally how numbers are presented. So if we're looking for 15 degrees, we have 0 degrees here, 50 degrees on the far left. So each line here looks like it represents 10 degrees. Each big tick mark represents 10 degrees. So 15 degrees would be right about there. Our pressure altitude today is 2,300 feet. Now note that the pressure altitude is found in the window, and it is measured or is indicated in thousands of feet. So if you see the number 5, that represents 5,000 feet. If you see the number 10, that represents 10,000 feet. So if we're looking for 2,300 feet, that would probably be right about there. So you have to align that 2,300 with the 15 degree temperature, which we will do now. Looks like right about a little bit more, right about there. That's probably as close as we're going to get. So we've got, again, our temperature of 15 degrees right here, and about 2,300 foot pressure altitude right there. So now if we look above, in the window above, we can determine our density altitude. Points to the density altitude right here of about, I'd say, 2,900 or 3,000 feet. So that would be your density altitude. Now, to determine our true airspeed, again we said calibrated airspeed was on the B scale, true airspeed is on the A scale. So our calibrated airspeed was 150, which is right here. Therefore, our true airspeed would be above that, and it looks to be about 157 knots. True airspeed. In the next example, let's say we know what our true airspeed is, but we don't know what our calibrated airspeed is, so we can do the same thing to figure that out. We have a known temperature of 30 degrees Celsius and a pressure altitude of 5,000 feet. So we will align our 30 degrees Celsius with the number 5 on the pressure altitude window. Let's see, right about there. So now we have 30 degrees Celsius right here, aligned with 5,000 feet pressure altitude. The true airspeed is 230 knots. Remember, true airspeed is on the A scale, so we will use the number 23 to represent 230 knots. And the calibrated airspeed will be read on the B scale, so that looks to be about 205. 205 knots calibrated airspeed. So that's quite a big difference compared to our first example where there was only a difference of 7 knots. This example we have a difference of 25 knots. So as we move faster and higher, the difference between your calibrated and true airspeed is going to be much greater. But you can also read the density altitude from this problem on the in the density altitude window right about here. It appears to be, I would say, about 7,600 feet density altitude. In the last example, we have a known calibrated airspeed of 100 knots, a temperature of -10, and a pressure altitude of 1,000 feet. So this seems like a pretty average day in Grand Forks. We can align our pressure altitude and temperature, so -10, so we're looking on the right side of the zero now. And we're going to line that up with 1,000, which would be right there. So we've got 1,000 feet represented by this tick, and -10 represented by this tick mark. The density altitude we can read above, so that looks to be right about -2,000, -2,000 foot density altitude. So your aircraft's going to perform very well today. Our calibrated airspeed was 100 knots. Remember, calibrated airspeed is on the B scale. 100 knots we find right here. True airspeed is on the A scale above. So it looks to be about 97. 97 knots true airspeed. So only a difference of 3 knots. So we can see that as we are lower to the ground, or lower altitude I should say, the difference between true and calibrated is negligible. Okay, next we are going to use E6B for some altitude corrections or conversions, however you want to view it. We can use E6B to convert between our pressure altitude and true altitude and calibrated altitude. So review of what those terms mean. Remember, the pressure altitude, as we said earlier, is the height above the standard datum plane. So whatever altitude the pressure of 29.92 is located today, your height above that altitude is your pressure altitude, and it is a somewhat reliable indicator of how your aircraft will perform. The indicated altitude is the altitude that's read directly from your altimeter. So hopefully you're setting the altimeter correctly, and you will have a fairly accurate indication of true altitude. Keyword there is fairly accurate. And that is as long as the temperature is reasonable. Let's put it that way. Calibrated altitude. So calibrated altitude is your true altitude corrected for instrument error. Again, just like the airspeed indicator, the position of the static port can never be in a perfect spot. So there's always going to be some difference between your indicated altitude and your calibrated altitude. But usually that difference is fairly negligible. Um, so the calibrated altitude is your indicated altitude that's corrected for instrument error. Now, previously I said the calibrated altitude is your true altitude corrected for instrument error, which is usually true. So as long as the temperature is reasonable and you are setting the altimeter correctly, your indicated altitude should be reasonably close to your true altitude. So true altitude is your height above mean sea level, and again, if you're using the altimeter correctly, that's what your altimeter should be reading. Now, the altimeter, we can correct the altimeter for non-standard pressure by using the Colesman window. That's where we set our altimeter setting. So that corrects for that non-standard pressure and gives us a more accurate reading of true altitude. Unfortunately, in most altimeters, we cannot correct for temperature. Temperature also has an effect on the reading within your altimeter. So because we can correct for pressure but not for temperature, our altimeter is not necessarily a really accurate indicator of true altitude when the temperature is really, really cold, or the air is really, really dense. So again, when the temperature is reasonable, so that, let's say, minus 10, 0 degrees, 10 degrees, anything hotter than that, the difference, the effect that temperature has is relatively minor. But as we get into very cold temperatures, let's say minus 25, minus 30, minus 40 degrees, that temperature can have a significant effect on your altimeter. So while your altimeter may be indicating that you are at a true altitude of 3,000 feet, you may actually be much lower than that. So we'll go through a couple of examples here, and hopefully it'll make a little bit more sense. So the A scale, if you look at the E6B, the A scale is labeled true altitude right here, and the B scale is labeled calibrated altitude. Remember, calibrated altitude is your indicated altitude corrected for instrument error. For the sake of simplicity, and because the difference between calibrated and indicated altitude is very marginal, we will simply assume that calibrated altitude equals indicated altitude. So according to the instructions on the face of the E6B on the left side for altitude correction, we need to set our pressure altitude opposite our temperature using the window on the left side of the E6B. That's important, we use the window on the left side, not the right side. And then we can make our altitude corrections using the A and the B scale. So for example, let's say we have a pressure altitude of 1,200 feet, a temperature of 15 degrees Celsius, and a altimeter reading, so we'll call that an indicated or calibrated altitude of 3,500 feet. So again, the pressure altitude is indicated in thousands of feet, so the number 10 here represents 10,000 feet. So this tick mark here, this small one, would represent 1,000 feet. Our temperature is in its raw format, so minus 20 equals minus 20. So we're looking for 15 degrees. It would be obviously on the right side of the zero there. So if we adjust our E6B, we will find 15 degrees. It's pretty close, right about there. So we have our temperature of 15 degrees, which would be right here. And that's pretty closely aligned with about 1,200 foot pressure altitude. Now, if we have a altimeter that shows 3,500 feet, we would be looking on the B scale, Remember, we're considering calibrated and indicated altitude to be essentially the same thing. So on the B scale, we're looking at 3,500 feet. We'll use the number 35 to represent that. So above that should be the true altitude, and that looks to be about 3,560. Let's call it that. This tick would represent the number 36. So a little bit of a difference there between your calibrated altitude or indicated altitude and your true altitude, but not much, right? At a reasonable temperature of 15 degrees, it's really only a difference of maybe 60 feet, which should not be too much of a concern. Now, in the next example, this is where this is an example of where this could be an issue, especially for IFR flight. So when you're flying IFR, you may be coming into land at an airport using an instrument approach, where you cannot actually see the airport until you're very low to the ground. A lot of the times, the minimum altitude on these approaches is often as low as 500 feet, 300 feet, 200 feet. An ILS approach usually gets you to about 200 feet above the ground. So if your altimeter is not quite accurate, that could be a problem when you're that low to the ground. So we've got a classic example here with a pressure altitude of 500 feet and a temperature of minus 40 degrees Celsius. Standard winter day, Grand Forks. So if we look on the left side of the E6B, we'll align our pressure altitude with our temperature. Minus 40, going the wrong way there. Right about there. That's pretty close. There we go. Yeah, lost it. There we go. So, we got our temperature minus 40, and that's pretty closely aligned with about 500 feet for our pressure altitude. Now our altimeter is telling us that we are at 200 feet. So we would assume, if the altimeter was reading correctly, we would assume that our true altitude was also 200 feet, but we will discover that is not the case. So the calibrated altitude is read on the B scale. So 200, we can use the number 20 to represent 200, and then the true altitude is on the A scale, and you'll see that that is about 164, probably 164 feet. So your altimeter says you're 200 feet above sea level, but in reality you're only 164 feet above sea level, which, if there's any type of obstacle below you, that could be a bit of a problem. So this correction is probably not something you will really use that much in VFR flight, since you can hopefully see the obstacles. But again, once you get to IFR flight, you often have to make corrections like this when you're flying an instrument approach on an extremely cold day. So hopefully that made sense. I understand that some of these concepts we talked about in this video are a little bit difficult to understand. So if you have questions on that, feel free to let me know and we can talk about it. But the next video is going to be much easier. We're going to do some basic conversions for distance, fuel calculations, weight, and temperature.